Hello students, in the last class we have seen the 5 important questions from unit 3. Now this is one more important question from unit 3, as well as this question may come from unit 4 also. Okay, so this is two kinds of question. We can give the same proof for these two kinds of question. See here, if R is a commutative ring with unity and A be a ideal of R, then prove that R by A is a field if and only if A is maximal. R by A is a integral domain if and only if it is a prime ideal. Okay, here you have to remember that R by A is nothing but an ideal of R. Okay, suppose if in place of A, if they give N also, we must write down the same proof. Instead of A, we must write down the N. Okay, so this question may come in 2-3 kinds, but you must write down the same proof. Okay, this question may come from unit 3 or unit 4. Just you remember that here R by A, the factoring R by A, here A is nothing but an ideal of R. If A is an ideal, you must write down this proof, right? Now here they are asking us to prove if and only if condition. So if R by A is an integral domain, if and only if A is a prime ideal. Okay, so first we will consider A is a prime ideal, then we will prove R by A is an integral domain, and conversely we will assume R by A is an integral domain and we will prove A is a prime ideal. Okay, very important question from unit 3 and 4. Right, so given R is a commutative ring with unity. Okay, so it is a commutative ring with unity, it is an ideal ring, so A is not equals to R. Okay, A is not equals to R, A is nothing but an ideal ring. So what we are going to prove? We are going to prove if and only if condition, means integral domain and A is an prime ideal, right? So first we will consider A is a prime ideal, then we are going to prove R by A is an integral domain. Okay, so before that we will take that R by A is nothing but an commutative ring. So since R is a commutative ring and A is an ideal of R, so what is a R by A? Factor ring, we are going to write it as A plus A, such that our A belongs to R. A belongs to R. So if A plus A and A plus B represent any two elements of R by A, so I am taking two elements from the factor ring, then A comma B belongs to R. A plus B, which is equals to A plus AB, A plus BA. Since here already they have given that R is a commutative, what we are going to prove? R by A is a commutative. Okay, so in R by A, how the elements are? In R the elements are A comma B, but in R by A, how the elements are? A plus A and A plus B. Now these two we are going to prove it is a commutative, right? So here what happens? A plus B is equals to A plus B, A plus A. So that R by A is a commutative ring. To prove R by A is an integral domain, first of all we are going to prove R by A is a commutative ring. Okay, so now we need to prove we are assuming A is an ideal of R and we are proving R by A is an integral domain. What is integral domain definition? Already I have discussed in the previous classes that it should have non-zero divisors, then we can say that it is an integral domain, right? So the zero elements of the ring R by A is the residue class A itself. So A plus B is equals to A. I can write this one as A plus AB is equals to A, therefore AB is equals to A, right? So here I can say that either A or B is in A. Okay, what is the prime ideal definition? Okay, what is the prime ideal definition? If AB belongs to A, either A should belongs to A or B should belongs to B. You have to remember prime ideal definition, either A should belongs to A or B should belongs to A. From here I am writing either A plus A is equals to A or A plus B is equals to A. Okay, right, either A plus A or A plus B is the zero element of R by A. If any one of this equals to A, one of the element will be compulsory the zero element. Okay, so either of any two is a zero element, no, so therefore R by A has no zero divisors. It has no zero divisors. If it has no zero divisors, therefore R by A is an integral domain. Okay, we took A is a prime ideal and we have proved R by A is an integral domain. Now conversely we are proving R by A is an integral domain. We are considering R by A is an integral domain and we are proving A is an prime ideal. Okay, to prove this one we must show that either A belongs to A or B belongs to B. Okay, if the product belongs to A, right? So we need to prove A is an prime ideal of R. Okay, right. So let A comma B represent any two elements in R such that AB belongs to A. Okay, so A plus AB is equals to A. I can write this one as A plus A into A plus B is equals to A. So already we have considered that R by A is an integral domain, so which has no zero divisors. Okay, it has no zero divisors. So if it has no zero divisors, I can say that either of any these two is 0. Either of any these two are 0. Okay, so A plus A is equals to A or A plus B is equals to A. Either A belongs to A or B belongs to A. Therefore A is a prime ideal. Similar steps. Okay, from back you can just go through of this above one, because here we have considered it is a prime ideal, we have proved integral domain. So first here we are considered R by A is an integral domain and here we are proving A is an prime ideal. Okay, this is a one of the most important question from unit 3 as well as unit 4. Okay, remember students, instead of A, if they are giving N or M, but you must remember that A is an ideal of R. Okay, right, thank you.